Okay, good morning. So let us solve problems in homework number 6, which is about mathematical induction, as you know. Okay, the first question, use mathematical induction to prove that for every natural number n, this relation holds. Okay, so let me write it on the board so that we can continue there. Okay, so the first problem, we are supposed to prove this equality. So I call it P of n. And what I have to do first is to check if P of 1 is true or false. I have to see actually it is true. So P of 1, it means that the left-hand side becomes 5 over 1 to 1 times 2 times 3. The right-hand side, I replace n with 1. So it becomes 1, 3 times 1 plus 7. And the denominator 2 times 1 plus 1 and 1 plus 2. Okay, but let me simplify this in an equivalent way. This becomes simply 5 over 6 equals to, this is 10 times 1, 10 over 3 times 2 times 2 is 12. And of course, 5 over 6 is evidently equal to 10 over 12. So this statement is indeed true. Now I will consider k to be a given natural number, and I myself assume that p for that particular k is true. So I have to write p of k, which is extremely easy task to do. Just replace letter n with letter k. So, but of course, you need to understand why mathematical induction method works in the first place, which we extensively learned about during the lessons. Okay, and then this becomes k plus 4 over k times k plus 1 times k plus 2, and the right hand side the same, so k times 3k plus 7 over 2k plus 1 k plus 2. And we assume that this is true, so assumed to be true. So what does it mean? It means that this responsive, if you want to say it in a different language, I would say that the responsibility of if this is true or false is not on us. Someone has given us this information. They say that, okay, assume that this is true, but you don't need to check if it's really true or false. Then you should show that, yes, if this is true, I can push this one step forward, and I should be able to prove that the same statement is also true for the next natural number, which is k plus 1. So I have to write it down. So I have to replace k with k plus 1 everywhere. So it becomes 5 over 1 times 2 times 3 plus 6 over 2 times 3 times 4. And then it will continue. If I replace k to k plus 1, this simply becomes k plus 5. Then this becomes k plus 1. The next one becomes k plus 2, and the next one becomes k plus 3. But based on the experience you got so far, you know that the problems involved with these 3 dots, it's always helpful to write the previous step as well. But the previous step is the step for number k, which is exactly this expression. So we learned about these things during the lesson a lot, so I don't want to spend time on it. But on the right-hand side, I have to replace every k with k plus 1. So this k becomes k plus 1. You have to remember to put it in pair of brackets. For example, here, I have to replace k with k plus 1, but not in this way. This is also a common mistake sometimes. So you have to put a pair of brackets around that. So this means that 3k plus 3 plus 7, so it becomes 3k plus 10. And the denominator is simple. It becomes 2k plus 2, and then k plus 3. Okay, this is to be proven. Okay, so going from here to here, I should prove this using this assumption and every other math knowledge that I have acquired before this. Okay, so I want to prove that this equality holds, so it means that I want to prove that the left-hand side of this equality equals to the right-hand side. So if you don't mind, let me start from the left-hand side and try to reach to the right-hand side. In the middle of the way, I need to use this assumption. Okay, so I would write the left-hand side. The left-hand side is this expression that you see here. So let me write everything in front of you. 1 times 2 times 3. This continues up to these two last terms. K plus 4 over k times k plus 1, k plus 2, and then plus k plus 5 over k plus 1, k plus 2, k plus 3. Okay, but how can I continue? I can immediately realize that instead of this part, I can use the assumption. Yes? According to the what I assume to be true, this left-hand side is equal to this expression. So instead of this one, I write that expression, and it becomes k times 3k plus 7 over 2 times k plus 1 times k plus 2. And then plus, I will write this one as well. So it is k plus 5 divided by k plus 1, k plus 2, k plus 3. Yes? Okay. Now my goal is to simplify this to reach to the other side. Okay? So here on the right hand side, I have one fraction, but here I have two fractions. So at least it motivates me to take the common denominator to combine them into one fraction. So to do that, I need to find LCD. So LCD is an expression. So for finding LCD, as we also learned in the number theory part for numbers, but that is also the same for polynomials. So this fraction involves with three factors, 2k plus 1, k plus 2, and this one has three factors, k plus 1, k plus 2, k plus 3. So if I ask you what factors you see in total, common or uncommon ones, 2 is one of them, k plus 1 is one of them, k plus 2 is one of them, k plus 3 is also one of them. So don't multiply them. Of course, if you multiply them, that is also a common denominator, I agree, but that is not the least common denominator, and it makes the problem a little bit much more tedious, I would say. So try to learn how to find LCD. So LCD is the common and uncommon factors with the highest power. But of course here 2 appears with power 1, power 1, power 1, power 1, power 1, power 1. So it means that the highest power for each factor is exactly 1. So that is exactly my LCD. And then I start comparing my LCD with the denominator of the first one. Which extra factor you see, this are there, so this is extra factor. So this extra factor should be multiplied into the numerator of the first fraction. So the first fraction has this as the numerator, so I have to multiply it by that extra factor I discovered. After that, I have plus. I will do the same thing. I compare my LCD with the denominator of the second one, but then you see that there is only a factor of 2 extra there. And that factor should be multiplied into the numerator of that second fraction, so it becomes 2 times k plus 5. Okay, but still, we have to do something to go from there to here. It's not exactly this one, of course, yet. So one thing comes to mind is to expand. Not denominator, because the denominator is already in factorized form, and you know that to simplify fractions, rational expressions, we need to put them in factorized form. The denominator is already in factorized form, so I really don't need to change anything there. But the numerator is not a factorized form because it's a sum. So let me open it up. So I multiply k inside because there are three expressions. I multiply k inside first, so it becomes 3k squared plus 7k. And then I have to multiply it by the next factor. Here I multiply 2 in, so it becomes 2k plus 10. And now what we do, we continue and then multiply this once more. So 3k cubed Okay, and then this one multiplied by that one is 9k squared. Remember that? 7k times k is 7k squared. With that 9k squared becomes 16k squared. But they also have to multiply 7k by 3k, becomes 21k. But there is a 2k here, so it becomes 23k's. And then at the end, I have a 10, and then divided by 2 times k plus 1, k plus 2, k plus 3. Okay, but still, this is not this answer. The direct way is to factorize the numerator and then see that if there is any common factor between the numerator and the denominator, and then cancel them out. But factorizing a third-degree polynomial in general is not an easy task. We will learn a little bit about how to factorize polynomials of degree 3 and above when we study the last chapter in Ma5. But we haven't studied that yet. But I want to teach you how to cheat a little bit here. If you trust your calculations so far, it means that you haven't done something wrong. So on the other hand, you know that you want to reach here. Okay? If you compare these two, you can guess what the numerator should be, and then state it as a claim and prove your claim. It's not cheating, it's completely valid way of doing things, but I want to tell you how, because factorization is a little bit hard. So, can you guess what will happen here? If I have done everything right, I have to be able to reach at this. So it means that if I compare the denominator with the denominator here, I see that factor of k plus 1 should be gone. Okay, so definitely in the numerator, there should be a factor of k plus 1, which is responsible to take this k plus 1 away and makes my denominator correct. Okay, but I also want to have the numerator to be this one. So it means that I need another k plus 1, which remains in the numerator. So it means that essentially I need 2 powers of k plus 1, and then I also need 3k plus 10. Okay, let me repeat. Let us assume that I was able to show that the numerator can be factorized in this way. But hopefully you agree with me, then I am done. Why? Because if I can show the numerator is equal to this, what will happen? 1k plus 1 here will cancel that k plus 1 and makes my denominator exactly what I need. But a k plus 1 and times 3k plus 10 will be left in the numerator, which is exactly what I have. So by this way of cheating a little bit, you can understand that to make this claim. Now, so this is in a scratch paper, okay? So you write something like this. Now, I show that 3k cubed plus 16k squared plus 23k plus 10 is equal to that. Not by factorization, of course, as I told you. Of course, if you are good in factorization, do it, that's correct. But now I want to show it not by factoring, by expansion. So I would say that now the right-hand side of this claim, this RHS means this right-hand side of this claim, is equal to, let me expand. So this is a squaring rule. The first one is squared 2 times the first one times the second one, plus the second one is squared times 3k plus 10. And then I have to multiply again. So this becomes 3k cubed plus 10k squared plus 2 times this one is 6k squared plus 2k times 10, 20k. Yes. And then 1 times this and times that. So it is 3k plus 10. Now if I simplify it one step more, so it becomes 3k cubed plus these two becomes 16k squared. These two becomes 23k, and then I have 10, and that is my left-hand side. By left-hand side, I mean this left-hand side. Okay, then I am done. So in principle, you should write therefore therefore, after you prove this, this continues like this. You can bring an arrow here, something like that. This becomes k plus 1 squared, 3k plus 10, divided by 2 times k plus 1, k plus 2, k plus 3, and then do the simplifications. This one and that one are gone, so it becomes k plus 1, 3k plus 10, and then divided by 2 times k plus 2, k plus 3, and that is exactly equal to the right-hand side of the expression I wanted. Sure. Okay. Any questions? Good. So let us go to the next one. So the next problem, let x be a real number, use mathematical induction to prove that for every natural number n, this product, cosine x, cosine 2x, cosine 4x, up to cosine 2 to the nth x equals to this expression. Okay, be careful here. X is a real number, so I'm not allowed to do induction on a real number. I can do induction only on natural numbers, so the induction should be on variable n, of course. So let me write it on the board so we can continue there. Okay. I want to prove this, so as usual I call it P of n, and then first I check if P of 1 is true or false. But here you have to be a little bit careful. When I say P of 1, it's a common mistake. People take only the first term. But that's not the case, because if you give me n, I start with 2 to power 0, because this coefficient is 1, you can interpret that as 2 to power 0. Yes? So 2 power 0, 2 power 1, 2 to power 2, until I reach to 2 to the power n that you already gave to me. Yes? So now that you are giving n equals to 1, I have to follow the pattern so that I reach to 2 to power n, in this case 1, and then stop. Okay? So I have to start with cosine x. But the next step is, I haven't reached to 2 to power 1 yet. So I have to continue one or more step, then it becomes cosine 2 to power 1x, then I stop. So P of 1 on the left-hand side contains the first two terms. And on the right-hand side is easy. So I put the question mark here to see if this is true or false. I replace n with 1, 1 plus 1, 2, 2 to power 2, 4. Divided by 2 to the power of 2, 4, sine x. This I have to check. Okay. This is one of the examples that we have so far that P of 1 is not trivial at all. So we have to convince ourselves that is also true. But that is why this problem is a good problem, because probably this is the first example we have dealt in the lesson, so that P of 1 is a little bit of challenge itself. Okay, there are some formulas that tells you how to change a product between two cosines into into a sum or a difference of sines or cosines. You might be able to use those formulas, but these are not in the standard Swedish education system in math. So my intention was not to use those formulas. Of course, if you use those formulas in a correct way, you will deserve the points. But my point is to here start from the right-hand side and reach to the left-hand side. That one, we have the standard formulas in the formula sheet. So sine for x, I want to use this formula. Sine of 2 nu is equal to 2 sine nu cosine nu. And that is the double angle formula for sine. This is the way that it is written, but if you remember in the Ma5 lesson, I told you interpretation is important. It doesn't mean only 2v and 2 nu and v, nu will work. It means whatever angle you have here, you have half of it here and half of it there. Okay? So for example, for sine 4x, I can simply write 2 sine. This is an angle. divided by 2, it becomes 2x cosine 2x. Okay, so let me do that. So instead of numerator, I write 2 sine 2x cosine 2x divided by 4 sine x. So far, I can simplify only these 2 with this 4 2 times. But then I use the double angle formula for sine again here. Okay, so it gives me another 2 sine of half of the angle, this time x, cosine of half of the angle, again x, but then I have to copy and paste cosine 2x. Of course, I don't need to put the formula for the double angle of cosine, because by looking at the right, on the left hand side, I can see that cosine 2x is indeed needed. And then I have 2 sine x here. And now everything becomes very clear. So 2 and 2, sine x and sine x are gone. And what is left for me is just simply the product, which you can see exactly on the left-hand side. So at least I was able to confirm that P of 1 is a true statement. Again, the standard induction is always the same. So I would say that let us assume that K is any given natural number and assume that P of K is true. So I have to write this expression for K. I just simply replace n with K everywhere. So it becomes cosine x, cosine 2x, cosine 4x, and it continues up to cosine 2 to the power of kx equals to sine 2 to the power of k plus 1x divided by 2 to the power of k plus 1 sine x. This is assumed to be true. I want to show that only based on this fact and my previous math knowledge, I can push this equality one step forward and prove that for the next natural number, meaning k plus 1, this is again true. So I have to write this statement first in a correct way. And it continues until the k plus first level. So it becomes cosine 2 to the power of k plus 1. And of course, you know that for these dots, you have enough experience that it is always helpful to write the previous step. Oh, I forgot to put an X there. The previous step is, of course, this one. The right-hand side is just replacing k with k plus 1 everywhere. So every k plus 1 now becomes k plus 2. So this becomes sine of 2 to the power of k plus 2x. And then I have 2 to the power of k plus 2 sine x. This is to be proven. Yes? Okay, I will start again from the left-hand side here. So the left-hand side is cosine x, cosine 2x, up to cosine 2 to the n to the kth x, and cosine to the k plus 1x. This is my left-hand side, but you know that the product from the first term up to the kth term is given in the assumption. Yes. And I can replace it with that expression here. And then after that, I have this factor, extra factor. So what happens? It becomes sine 2 to the k plus 1 x divided by 2 to the k plus 1 times sine x multiplied by that extra factor. Okay? But that is now not that hard. I have to do it to reach here. The first thing comes to my mind, because I want to know what to do to reach here. So for example, I compare what I have in the denominator of what I want to show and what I have in the denominator so far. I can see that the sine x is exactly what I need, but I have 2 to the power of k plus 1. What I need is 2 to the power of k plus 2. So it motivates me somehow to make 2 to the power of k plus 2 appear here. And then it becomes easy. So I just rescale this fraction by a factor of 2. Okay, so what happens now? this will be 2 sine 2 to the power of k plus 1 x, and then the denominator becomes 2 to the power of k plus 2. So I rescale this fraction by a factor of 2. Now the denominator is exactly what I need, but I also have an extra factor. If I give a denominator 1, so it can go to the numerator. So if you don't mind, let me just extend this fraction line. So this becomes cosine 2 to the power of k plus 1 x. But now you see here, do you remember in the Math 4 lesson I told you that this combination sine box, cosine box is very famous, especially if you have also the extra factor of 2. Everything can be collected into the sine of 2 times what you see in the box. Yes? So now this will play the role of your box here because they are the same. So I can read it as 2 sine box, cosine box, which becomes sine of 2 times box. So it becomes sine of 2 times your box divided by, copy paste the denominator, but then immediately you can see what happens. Yes, these 2 to the power of 1 times that becomes 2 to the power of k plus 2, and that is exactly equal to the right hand side. Yes, is it? Sine to the power of 2k plus 2 times x divided by the same denominator. So that is the solution to this problem. Okay, now let us go to the next problem. Okay, so this is the next problem. Use mathematical induction to prove that for every natural number n, 1 plus 1 over 4 plus 1 over 9 up to 1 over n squared is less than or equal to 2 minus 1 over n. Okay, so if you haven't thought about the problem before, as I am erasing the board, you can think about it yourself. Okay, so this time I want to prove an inequality. Again, of course, I should call it P of n. And first check the truth of this statement for n equals to 1. So P of 1 is the left side just simply becomes 1. And the right hand side becomes 2 minus 1 over 1. But this is equivalent to saying that 1 is less than or equal to, this is also 1, which is of course true. Now I assume that k is a given natural number, and I assume that p is true for that particular k. Meaning that I assume that 1 plus 1 over 4 plus 1 over 9 up to 1 over k squared is less than or equal to 2 minus 1 over k, assumed to be true. Now I want to show that I can push this one step forward and prove that the same statement is also true for the next number k plus 1. So meaning 1 over 4 or 1 over 9 up to, instead of k, I write k plus 1. But again, based on experience, you know that it is always good to write the previous step, which is the kth step. And then less than or equal to 2 minus 1 over, replace k with k plus 1. And this is something we want to prove. Okay. Different teachers probably have different strategies for these things, for solving inequalities. So still, if you don't mind, let me start from the left-hand side. I want to convince you, based on this assumption, that the left-hand side of this expression is still less than or equal to this expression. So I will start from the left-hand side of what I want to show, which, let me write it again in front of our eyes. It continues up to 1 over k squared plus 1 over k plus 1 squared. So now what I want to mention is this. This is an expression composed of 2 parts. Let me consider this one part. Let me consider this another part. I copy and paste this part without any changes. But then I want to replace this expression with this one, But of course they are not equal, so I cannot put equality sign there. If I do that, I have to put less than or equal. I hope that this is understandable now, yes? What I'm saying is that this first part is less than this part, and this part is equal to this part. So it is obvious that the left-hand side is less than or equal to this. My goal is to continue in an ideal scenario, in an ideal case, my goal is to simplify this and reach to this one. But usually it is not possible. This ideal scenario does not happen for inequalities in most of the time. Okay, so let us simplify that. We have to change our strategy a little bit. But now I go equally. What I do, I look on the right hand side. There is a 2 here, so let me not touch that 2 there because I need it. So let me write that 2 here. But between these two, I take the common denominator, and because I need a minus sign probably here, I will pull the minus sign out, so this becomes positive, this becomes negative, and then I take the common denominator. The LCD is k times k plus 1 squared. Compare this one with this denominator. It becomes, this is the extra factor, should be multiplied there. And then I told you I pulled the minus sign out, so now this is minus. I compare this one with that one. I have one extra factor k, should be multiplied up there, so it becomes k. Okay, yeah. One desire is probably to continue and reach to this one, but you will see it will not happen. So let us simplify that. I do not touch this 2, I do not touch the minus sign. And you know that you shouldn't open it up, because if you want to simplify fractions, you want them in factorized form, so don't touch it, but let me open it up. The first one squared is k squared. 2 times the first one times the second one is 2k, but there is a minus k here, so it becomes just simply k, and then 1 to power 2 is 1. Okay, and this cannot happen, this cannot be factorized. This is a quadratic number. This is a quadratic polynomial, its discriminant is negative. If the discriminant is negative, you cannot factorize it in the realm of real numbers. So there is no hope that I can factorize it and the cancellation appears, yes? So I mean that if you want to use the cheating method that I told you before, you might go to a scratch paper and to see if it is possible to factorize this into a form that after simplification gives me this fraction. If this is going to happen, I need to have a k, I need to have a k plus 1 in the denominator. Yes? But this is not the case, because if I multiply that, it becomes k squared plus k, but this is k squared plus k plus 1. So this factorization is not possible. Okay, so what should I do? In inequalities, this very often happen. So my goal, let us go back here. Let me call this number capital A. Let me call this number capital C. What is my goal? My goal is to show that capital A is less than or equal to capital C. But I couldn't do that. But instead, you see, this is exactly capital A. So I was able to show that capital A is less than or equal to this expression, which I want to call it capital B. Okay? So what is happening? I wanted to show that A is less than or equal to capital C. I couldn't. Instead, I was able to show this one. Then I asked myself, what can I prove so that that one and this one combined gives me my result? It's very simple. If I can show that B itself is less than or equal to C, then I am done. It's not guaranteed yet, but this I know. This is the goal. I ask myself, is it possible to prove this? Because if I could, then A is less than B, B is less than C, of course, A is less than C. So now I focus my energy to prove that capital B is indeed less than or equal to capital C. So now you need to write a little bit of line here. So you say that now I show that a B, B, which is 2 minus k squared plus k plus 1 over k plus 1 squared is less than or equal to C, which is this combination. 2 minus 1 over k plus 1. Okay, I show that this. But then it is not that obvious that this is indeed true. Okay, so I have to start simplifying this inequality in a recursive manner. So I should be able to go back and forth between these transformations that I'm going to make now, and reach to something which is trivially true. Okay, so what happens now? I will simplify that. Of course, I have to put full stop here, then write it again if I really want to write precisely, but let us just continue from here. First thing is that, okay, these two, I move it to the left to come. So it means that I am left with this expression. Yes? But be careful. I put double-sided arrow. This is extremely important. It means that if I want, I can eliminate, go from here to here. If I want, I can add to, I can go backward, because it is extremely important that they go in an equivalent way. Okay, but now, if you don't mind, let me multiply by minus sign. When I multiply by minus sign, it will be flipped. So it becomes greater than or equal to that. And now I don't like fractions, so I multiply everything by k times k plus 1 squared, but because k is a natural number, this combination is definitely positive, so I'm not worried about the direction of the sign. So I can go in an equivalent way and multiply everything by k plus 1 squared. This will be cancelled. I will be left with k squared plus k plus 1. And now imagine that after multiplying the right-hand side by this expression will be in the numerator. So one factor and one factor will be gone. So it becomes greater than or equal to k times k plus 1. Okay? So that is, now I can go equivalently. So if you don't mind, let me write the continuation here. I open it up, so it becomes k squared plus k plus 1 greater than or equal to k squared plus k. And then I move these two to the left. They are cancelled, so it becomes 1 greater than or equal to 0. So this double-sided arrow means all statements that you can see are equivalent. It means that either they are simultaneously true or they are simultaneously false. This is the meaning of being equivalent statements. Okay, so this means that this statement has the same truth value as this statement. But this is trivially true. So then it means that the original statement is also true. So it means that I was able to show B is less than C. I was able to show that A is less than B. Compared to these two, I will get my result back. I will get my results. Okay, any questions? Okay, so let us go to the last problem of this homework. So in the last problem, use mathematical induction to prove that for every natural number n, we have this. Okay, we want to show that 16 divides 5 to the n minus 4 times n minus 1. Okay, so let us go to the board. My goal is to prove that 16 divides 5 to the n minus 4n minus 1. So I call this a statement P of n. Then I check it for 1. This means that 16 divides 5 to the power of 1 minus 4 times 1 minus 1. But this number is just simply 0. So this is equivalent to saying that 16 divides 0, which of course we know is true. We learned that in number theory. So that is true. Okay? So K of 1 is true. Again, I assume that K is a given natural number. so that P of k is true, meaning that I know that 16 divides 5 to the k minus 4k minus 1. I want to show that I can push this one step forward and prove the same statement, but this time for k plus 1, means that I want to prove that this is indeed true. But be careful, you have to replace k with k plus 1 in pair brackets minus 1. So this is assumed to be true. And this is to be proven. Okay, but of course, because algebraically I can make this a little bit simpler, I prefer to work with something equivalent. I will copy and paste 16 divides, but 5 to the power of k plus 1 minus 4k minus 4 minus 1, which is minus 5. So I concentrate on working this red one, okay? Again, I will prefer to start from here. I have seen different teachers have different attitudes. You can also find the one that suits you best. But if you don't mind, let me start from here. So 16 divides 5 to the power of k minus 4k minus 1. So what does it mean? It means, according to what we learned in number theory, there exists an integer such that the number on the right is 16 times this q. This is what we know. And now we know that somehow I have to manipulate this so that this expression appear. Okay, this is not a hard task because we did some very good examples when we were dealing with number theory. I don't think it is hard for you to understand that I would compare 5 to the k with 5 to the k plus 1, what I need, so it motivates me to multiply by 5, everything by 5. So if I multiply the left-hand side by 5, it becomes 5k plus 1, the next one becomes minus 20k, the next one becomes minus 5, and then of course you know that it becomes 5 times 16 times q. Of course you can write also 80, but based on that experience you know it is not necessary. Okay, of course we fixed two parts of it, you know, if it was 5 to the k and minus 1, okay, and minus 4k. If I compare this one with what I need, minus 4k was correct. But by this multiplication, I fixed the first one, 5 to the power of k plus 1, and then the last one also becomes minus 5, that is good, but unfortunately, this is inevitable. I have to change minus 4 to minus 20. Yes, that is not under my control. When I multiply by 5, this will be the case. But based on the experience, you know, I want to get rid of extra factors here. So it motivates me this time to add 16k to both sides. If I add 16k here, I should also add 16k there, of course. I want to keep equality intact. But then the left-hand side at least becomes exactly what I need. So if I add them up, it becomes minus 4k minus 5. But the right-hand side, between these two, I can factor a 16 out. Then it becomes 5q plus k. What matters, I don't know q, I don't know k, but what matters to me here is that this combination should be an integer, and it is. Because q was an integer, k was a natural number, so that is definitely an integer. So what does it mean? This means this number is an integer multiple of 16. It means 16 divides 5 to the power of k plus 1 minus 4k minus 5, and that is exactly what I wanted to show. Okay, any questions? Okay, thank you.